All right, let's go over part number 2 on the gas laws and review questions. So number 1 says heat in a contained gas that's held at a constant volume increases its pressure. Why is that? So you have a contained gas, right? It's inside of a container, which means inside of a balloon or inside of an aerosol can. Right? If you heat it, raise the temperature, why does the pressure go up? Well, those particles are going to hit harder. They're moving faster inside there, and they're going to hit harder on the inside of the container. So hitting harder increases pressure. Kind of like, remember in the notes, the whole idea of walking into a wall or running really fast into a wall. If you're moving faster, you exert a greater force. And those particles will be moving faster. If they increase their temperature, they have more kinetic energy. Number 2, what happens to gas particles when a gas is compressed? Compressed means we're going to take a gas in a balloon and we're going to make it smaller. All right, that means compress it. So if I compress it, that means there's going to be more collisions with the particles with the inside wall. So what's going to happen is the pressure is going to go up. All right, when it's way out here, there's less collisions with the wall because they're bouncing all over the place. Squish them all down, and all of a sudden they're bouncing all over the place, and we're going to increase the number of collisions, and I have higher pressure. Number 3, a metal cylinder contains 1 mole of a nitrogen gas at STP, standard temperature and pressure. What's going to happen to the pressure if we double the amount of gas? In other words, add another mole of the gas in the cylinder, but the temperature and the volume don't change. So right now I got this container, and I'm going to go, I'm going to add more to it. It's not going to get bigger, right? So I'm not going to change that, not going to change the temperature. Well, now all of a sudden I got more particles in there. I'm going to have more collisions. More collisions means higher pressure, all right? Number 4, if a gas is compressed from 4 liters down to 1 liter, and the temperature remains constant, what happens to the pressure? Big down to small, increases collisions, increases pressure. Number 5, why is Kelvin temperature specified in calculations that involve gases? It's all because it's a direct relationship to the kinetic energy. I'm sorry, excuse me there for a second. But Kelvin temperature is directly related to kinetic energy. So as I raise the kinetic energy, I raise the Kelvin temperature. As I lower the Kelvin temperature, I lower the kinetic energy until I go all the way down to absolute zero where there's no kinetic energy. So Kelvin temperature is a direct relationship to the amount of kinetic energy that are in the particles. Number 6, describe what happens to the volume of a balloon when it's taken outside on a cold winter day. So it's cold out, those particles are going to slow down. As they slow down, then the volume is going to go, and it's going to get smaller, like the idea of carrying the balloon out of Myers on a cold winter day. So the particles slow down and the balloon gets smaller. All right, number 7, we got to do some math. So let me turn my lights back on. Hold on. There we go. All right, we'll get rid of this. All right, we're going to make our little chart. We got P, V, and T. And we got system 1 and system 2. So the first question says the gas in a closed container has a pressure of 300 kilopascals. So we got 300 kPa. And that's at 30 degrees Celsius, or 303 Kelvin. And then it says what will be the pressure if the temperature is lowered to 101 kPa. So we want to find out this. So remember, we have PV over T equals PV over T. That gives me every equation that I need. Oh, let me move this up a little bit so you can see it a little better. There we go. So I'm working with P and T. So P and T, they're on top of each other. So I have 300 over 303 equals X over 101. So cross multiply. So I get 303 times X equals 300 times 101. I get X by itself, so divide by 303. So X ends up equaling, X equals 100. That's 100 kilopascals is the answer. All right. Second one, next one after that. Number 8, calculate the volume of a gas at a pressure of 1,000 kilopascals if its volume at 120 kilopascals is 1.5 liters. So let's go back and clear this off. And clean this out. Okay. So we have calculate the volume of a gas at a pressure of 100 kilopascals. So we have 100 kilopascals. And they want us to find out the volume. If its volume at 120 kPa is 1.5 liters. So this time temperature is staying the same. So we're going to be able to keep temperature out of there. So we're going P times V equals P times V. So this times that equals this times that. So we got 100 times X equals 120 times 1.5. So I gotta get X by itself, so divide both sides by 100. Now let's get rid of that. And X ends up equaling, the right answer is 1.80 liters. So, and we look at this and again decide whether or not this makes sense. That pressure went from high, went down over to here. So what should the volume do? Well, the pressure goes down, and that means the balloon got bigger. So we went 1.5 up to 1.8. So yep, it did get bigger, so that's okay. All right, so we did that one right. Let's clear this out. All right, next one. A gas with a volume of 4 liters. So we got a volume of 4.0 liters at 90 kilopascals. Expands until the pressure drops to 20. So the pressure goes down to 20 kilopascals. We want to find out what's the new volume, given that the temperature stays the same. So the temperature we get to ignore, so that means we get rid of the temperature, we're doing P times V. So 90 times 4 equals 20 times X. So we gotta get X by itself, so divide both sides by 20. That gives me X all by itself. So when you divide this out, you get 18. And we were after volume, so that's liters. So looking to see if this is right, the pressure went from 90, went down to 20. So, all right, so in order to make it go down, I gotta make this thing bigger. So it went from 4 up to 18. Yep, it did get bigger. So that follows the rules. All right, on to the next one. Clear this guy off. All right, number 10. A gas with a volume of 0.3 liters. So we got 0.300 liters at 150 degrees Celsius. So 150 degrees Celsius is heated until its volume is 0.6 liters. We want to find out what's the temperature that it became. All right, this time the pressure stays the same. So we get to get rid of pressure, so we're going V over T equals V over T. So 0.300 divided by, whoops, we got to fix this temperature. It's got to be 273. So that's what, 312, 423 Kelvin. So 423 Kelvin equals 0.600 over X. Now know that when we do this, we're actually finding out the temperature in Kelvin, not in degrees Celsius. So cross multiply. So 0.300 times X equals 0.600 times 423. You gotta divide by 0.300, divide by 0.300. That gets rid of those guys. X equals 846 Kelvin. So my temperature went up. Well, my temperature went up, then that means my volume should go up. Yep, it did. Okay. Takes me on to the next one. Number 11. Why do aerosol containers display the warning, do not incinerate? On that one, why does that happen? Incinerate means burn. So remember that aerosol cans, that's these things, right? And if you heat those things up, the particles inside get moving so hard and they can explode. That's why you don't want to incinerate them or burn them. Number 12, state the combined gas law. Well, the combined gas law, that's that thing up there. PV over T equals PV over T. And combine means it combines Boyle's, Charles, and Gay-Lussac's, all three of them together. All right, we got a sealed container of gas, number 13, of nitrogen gas at 1,000 kilopascal pressure at a temperature of 20. The cylinder is left in the sun, and the temperature of the gas increases to 50 degrees. What's the new pressure? Oh, we're back to a problem again. So we're going to erase all this, and we'll erase this. All right, so we've got 1,000 kilopascals And that happens to be at a temperature of 20 degrees Celsius. And it says the cylinder is left out in the sun and it goes up to 50 degrees Celsius. We want to find out what's the new pressure. So volume staying the same, so we're getting rid of V, we're going P over T. So we got 1,000 divided by, oops, got to add 273 to this. So that's 293. And 273 to this is 323. So this is going to be over 293 Kelvin. Now we're finding X for the pressure over 323. All right, cross multiply. That times that, and that times that. 293 times X equals 1,000 times 323. Divide by 293, divide by 293. That gets X by itself. And if we solve that, we should get an answer of about 1,100. And that happens to be kilopascals, is what we're trying to find out. So that's what we should have for that one. 14, show how Charles's law can be derived from the combined gas law. All right, well, remember, I'm going to get rid of this now. Remember, we had three laws. We had Boyle's, Charles, Gay-Lussac's, right? And those go in alphabetical order. So Boyle's, we get rid of the T, and we get PV equals PV. So that's Boyle's law. Charles's law, we go clockwise, and we go up here and get rid of the P. So we get V over T equals V over T. Right? Gay-Lussac's law, we continue, we get rid of the V, so we get P over T equals P over T. So there's the three laws, actually. And all it is just removing something, which really why we're removing it, because it's constant. Once it's constant, then I don't need that piece in the mathematical expression, because it's not going to do anything to it. So, all right. 15, explain why it's impossible for an ideal gas to exist. So why can't I have an ideal gas? Because there's no such thing. Well, the reason is, remember that all gases become liquids and solids. And according to the ideal gas law, they're not supposed to do that. They're not supposed to become liquids or solids. All right, so that's the spot where they deviate away from that. All right. 16, describe an ideal gas. Ideal gases follow all the gas laws as long as they're a gas. So they follow all these, Boyle, Charles, and Gay-Lussac's law exactly all the time. All right, last one, number 17. So let's clear this thing out. And we'll clear this. So we've got 0.28 moles. Oh, we got to add that mole down here. So we got 0.28 moles. And we got a methane gas is introduced into an evacuated 2-liter container. So we got a 2-liter container at 35 degrees Celsius. And we want to know what's the pressure. So we want to know this. So this time we're using PV equals nRT, right? So we're not using this guy this time. So I have a pressure, we want to find out pressure. My volume is 2.0. N is 0.28 moles. R, if you remember in your notes, was 0.0821. That's a constant, never changes. Then the temperature, we got to add 273 to this. So that's 308. So times 308. All right, so I can divide by 2, divide this all by 2. That gets rid of that. And X ends up equaling something like, let's see, whoops, I got to flip it over so I don't have to do the math, but 3.55. And that was a unit of pressure. It happens to be atmospheres in this case. So you got 3.55 as your answer for that one. This one, notice that we only had one pressure, one volume, one temperature, right? Instead of like the other ones where we had 2 pressures, 2 volumes, and 2 temperatures. All right, that concludes the review for part number 2. So it's time for the test now pretty soon, probably tomorrow. So see ya.